Welcome to AP Statistics. Today, we are focusing on topic 3.13, carrying out a test for the difference between two population proportions. Our learning objectives are to calculate the z-test statistic and p-value, interpret the p-value in context, and justify a claim by comparing the p-value to alpha. By the end of this lesson, you will be able to perform a complete two-sample z-test to determine if there is a significant difference between two groups, such as whether a new medication works better than a placebo or if voting habits differ between two cities. Before we dive into the calculations, let's establish our framework. When we compare two population proportions, we are looking at the difference between P1 and P2. Our null hypothesis, H0, almost always assumes there is no difference. We assume the two populations have the exact same proportion of the characteristic we are studying. The alternative hypothesis, H alpha, depends on the question being asked. Are we looking for any difference, a specific increase, or a decrease? Our goal is to see if our sample data provides enough evidence to reject the idea that the proportions are equal. To do this, we need a test statistic that tells us how many standard deviations are observed differences from zero. To calculate our test statistic, we use a z-score. However, there is a special twist when testing the difference between two proportions. Since our null hypothesis assumes the two population proportions are equal, we don't treat the groups separately when estimating the variability. Instead, we combine or pool the data from both samples to get one overall success rate. This is called the pooled proportion, or p-hat combined. For example, if Group 1 had 10 successes out of 50 and Group 2 had 20 successes out of 60, our pooled proportion is 30 divided by 110. Notice how we simply add the numerators and the denominators. This pooled proportion is what we use to calculate the standard error for our test statistic. Now that we have our pooled proportion, let's look at the full formula for the z-test statistic. It looks a bit intimidating at first, but let's break it down piece by piece. The numerator is our observed difference between the sample proportions minus the hypothesized difference, which is usually zero. In the denominator, we have the standard error. Notice we use the pooled proportion, p-hat c, for both groups. We do this because the null hypothesis assumes the proportions are actually the same, so we use our best single estimate for that shared proportion. This z-statistic follows a standard normal distribution. A z-score far from zero suggests that the difference we observed is unlikely to have happened by random chance if the null hypothesis were true. We have now defined how to calculate the z-score. Next, we will see how to turn this value into a p-value to help us make a decision. Once we have our z-score, we need to find the p-value. The p-value is the key to our conclusion. The p-value is the probability of getting a sample result as extreme or more extreme than the one observed, assuming the null hypothesis is true. Think of it this way. If there really is no difference between the two populations, how lucky or unlucky would we have to be to get the data we just collected? The direction of our p-value calculation depends on our alternative hypothesis. There are three types of tests: right-tailed, left-tailed, and two-tailed. If we think proportion 1 is greater than proportion 2, we look at the right tail. If we think it's less, we look at the left tail. If we just think they are different, we calculate the area in one tail and double it. Remember, a p-value is not the probability that the null hypothesis is true. It is the probability of seeing our data given that the null hypothesis is already assumed to be true. To understand this better, let's walk through our first full example. Suppose a researcher wants to know if a new study method improves the pass rate of a difficult exam compared to the traditional method. In Group 1, 82 out of 100 students passed. In Group 2, 84 out of 120 passed. We will use a 5% significance level. First, we find our sample proportions. Group 1 has an 82% pass rate, while Group 2 has a 70% pass rate. There is a 12% difference. Is this difference significant or just due to the specific students we picked? Our null hypothesis is that the methods are the same. Our alternative is that the new method is better. Before the z-test, we pool the data. Combining both groups, we have a total of 166 passes out of 220 students. This gives us a pooled proportion of approximately 0.7545. Now, let's plug these values into our z formula to see how many standard deviations that 12% difference is from zero. We subtract our sample proportions in the numerator. In the denominator, we use that pooled proportion of 0.7545. After calculating, we find a z-score of approximately 2.06. This means our observed difference is over 2 standard deviations above what we would expect if the two methods were actually identical. Since our alternative hypothesis is that the new method is better, we look at the area to the right of 2.06 on the standard normal curve. Using a calculator or a z-table, we find a p-value of 0.0197. We have successfully calculated our test statistic and p-value. Take a moment to think about what this p-value actually represents before we move to the decision. Now we must decide, is this result strong enough to reject the null hypothesis? We do this by comparing our p-value to our significance level, alpha. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. In our exam study example, our p-value was 0.0197 and our alpha was 0.05. Since 0.0197 is less than 0.05, we reject the null hypothesis. When writing your conclusion on the AP exam, you must be very specific. First, compare p to alpha. Second, state the decision to reject or fail to reject. And third, state the evidence for the alternative hypothesis in context. Because our p-value of 0.0197 is less than alpha equals 0.05, we reject the null hypothesis. There is convincing statistical evidence that the true proportion of students who pass using the new study method is greater than the true proportion of students who pass using the old method. Notice how we used non-definitive language like convincing evidence rather than saying we proved the new method is better. In statistics, we never prove anything. We only find evidence for or against a claim. Let's try a second example to practice interpreting the p-value more deeply. This time, let's look at a public health question. Is there a difference in the proportion of adults who exercise regularly in City A versus City B? In City A, 110 out of 200 adults exercise. In City B, 150 out of 250 exercise. Our null hypothesis is that there is no difference in exercise rates. Our alternative is that there is a difference. Note that this is a two-tailed test because we are looking for any difference, not just one being larger. First, we calculate the pooled proportion. Combining both cities, we have 260 successes out of 450 people, which is approximately 0.5778. Using our formula, we find a z-score of approximately -1.07. This means the observed difference is about 1 standard deviation below 0. Before we find the final number, remember what the z-score represents. It tells us that City A's sample proportion was slightly lower than City B's, but not by a massive amount. Now let's see how likely this result is under the null hypothesis. Because our alternative hypothesis was that the proportions are simply not equal, we must account for both tails of the distribution. The area to the left of -1.07 is 0.1423. Since this is a two-tailed test, we double that value to get a total p-value of 0.2846. Visually, we are looking at the probability of getting a difference of 5% or more in either direction. This interpretation is crucial for the AP exam. We must clearly state that we are assuming the null is true. A p-value of 28% is quite high. It happens almost a third of the time just by random luck. Since our p-value is greater than our significance level of 0.05, we fail to reject the null hypothesis. We do not have enough evidence to say the exercise rates are different. Notice, we don't say the rates are the same, we just say we haven't found enough evidence to prove they are different. Let's look at one more scenario to really cement these skills. This time, imagine a tech company is testing 2 different layouts for their website to see which one leads to more signups. In layout X, 75 out of 500 users signed up. In layout Y, 55 out of 500 users signed up. The company wants to be very sure before making a change, so they use a strict 1% significance level. The company's claim is that layout X is more effective. Our null hypothesis is that the layouts perform the same. The pooled proportion is simple here. Combining both groups gives us 130 signups out of 1,000 total users, or exactly 13%. We calculate our z-statistic and find it is approximately 1.88. This indicates that layout X's 15% rate is nearly 2 standard deviations above layout Y's 11% rate. We have our z-score. Now, let's determine if this 4% difference is enough to meet that strict 1% alpha threshold. With a z-score of 1.88 and a right-tailed test, we calculate the area to the right. The p-value is 0.0301. Now, Let's compare this to our alpha. Even though layout X performed better in our sample, the p-value of 0.03 is larger than our alpha of 0.01. Because the p-value of 0.0301 is greater than alpha equals 0.01, we fail to reject the null hypothesis. There is not convincing statistical evidence that the true proportion of signups for layout X is greater than the true proportion of signups for layout Y. Take a moment to think about why we reach this conclusion despite the higher success rate in layout X. This is a great example of how the significance level affects our results. If our alpha had been 5%, we would have rejected the null. But because we chose a stricter 1% level, we require more evidence than what this sample provided. This highlights why transparency in choosing alpha is so important in real-world research. Let's review the common pitfalls that students often face when performing these tests on the AP exam. First, remember that pooling is required for the difference between two proportions when testing the null hypothesis that they are equal. If you use the individual sample proportions in the denominator instead of the combined p-hat, your standard error will be slightly off. Second, always draw a normal curve. It helps you visualize whether you should be looking for the area to the left, the right, or both. If your alternative hypothesis is not equal, and you forget to double the tail area, your p-value will be half of what it should be, which could lead to an incorrect decision. Finally, avoid the word prove. In your conclusion, always say we have convincing evidence for the alternative, or we do not have convincing evidence for the alternative. Saying we proved the null is true, or we proved the alternative is true, is a major conceptual error. By following these steps, state the hypotheses, calculate the pooled proportion, find the z-score, determine the p-value, and compare it to alpha, you will be able to justify any claim about the difference between two population proportions. To ensure you're fully prepared, let's work through one more comprehensive example, paying close attention to the details of the standard error calculation. Imagine a study investigating if a certain medication reduces the risk of side effects more effectively in women than in men. In this study, 45 out of 150 men reported side effects, which is 30%. In the group of women, 40 out of 200 reported side effects, which is 20%. Our null hypothesis is that the side effect rate is the same for both. Our alternative is that the rate is higher for men. Combining the groups gives us 85 total reports of side effects out of 350 participants. This results in a pooled proportion of 0.2429. Notice how this value falls between our two sample proportions of 20 and 30%. Before we calculate, take a moment to guess. We have a 10% difference with several hundred people. It feels significant, but the math will tell us for sure. Now, let's execute the final calculation. We need to find the standard error and the resulting z-score to determine our p-value. The standard error is approximately 0.0463. This represents the typical distance we would expect the difference in sample proportions to be from zero, just due to random sampling variability. Our observed difference of 10% is 2.16 standard errors above zero. Using our calculator, or z-table, the area in the right tail is 0.0154. We have our p-value. If the medication side effect rates were truly identical for men and women, we would only see a difference of 10% or more in about 1.5% of similar studies. Since this is quite rare, it provides evidence against the null hypothesis. Finally, we wrap up with our formal decision and conclusion. We must connect the p-value back to our significance level and the context of the medication study. Since our p-value of 0.0154 is less than our alpha of 0.05, we reject the null hypothesis. Notice how we state the conclusion in terms of the alternative hypothesis and clearly mention both populations, men and women. This is exactly what the AP graders are looking for. Let's recap our objectives. We calculated the z-test statistic and p-value, interpreted the p-value, justified claims using alpha, and used pooled proportions correctly. Take a moment to reflect on that. Why do we assume the proportions are equal before we even look at the data? We assume equality to establish a baseline or a boring world. Only when the data is weird enough to be unlikely in that boring world do we decide that something interesting, a real difference, is actually happening. You are now equipped to carry out a two-sample z-test for the difference between two population proportions. Remember, pool your proportions, check your tail direction, and always conclude in context. Good luck with your studies.